So there are two motivations. So I'm going to talk about cohomological Hall algebras. And I think there are two main motivations to study cohas. One of them comes from enumerative geometry, Donaldson-Thomas invariants, moduli spaces of sheaves on Calabi-Yau threefolds, for instance. And another motivation, which I think at the start is completely independent, comes from representation theory. So what I hope to do today is to motivate for you the introduction of cohas from the point of view of representation theory. And in fact, but maybe we will see this later, the representation theory perspective provides a kind of the local picture for the 3 Calabi-Yau perspective, for the more enumerative geometry perspective. So the two are linked, but maybe you only discover this a bit later. OK, so motivation from, I say, representation theory of Kac-Moody algebras. Of Kac-Moody. So what I'm going to explain now is at least for much of it, pretty old. There are some good references about that, so I will not give too many proofs, but I will try to give an idea of proofs.
Better write a bit bigger.
Ooh, this is already big for me, but OK. OK. All right, so let me start by recalling a little bit about the Kac-Moody algebras. OK, this is more notations. So we start from a Dynkin diagram. And out of this Dynkin diagram, we can, well, a generalized Dynkin diagram, let's say. And out of a generalized Dynkin diagram, we can produce a Kac-Moody algebra. So G, let's say G gamma. So I will not recall the definition, but I will say a little bit about the structure. Kac-Moody Lie algebra. And then out of this Dynkin diagram, one can also put some orientation. Okay, orient the edges. And maybe do something a bit more fancy if the Dynkin diagram is not simply laced and you have some labels. But OK, let's not consider this case here. And then you get a quiver with a vertex set and an edge set. Quiver. OK. So what I want to do today is I want to explain to you how one can get information from Kac-Moody Lie algebras from the representation theory and geometry of quivers, and also vice versa. So I will first start by giving you some notations about Kac-Moody algebras, and then some notation about quivers, and then state some theorems, old and classical theorems that relate the two. OK, so Kac-Moody algebra, one of the important things about Kac-Moody algebras is that they are built from a set of generators with a certain set of relations that come from the Dynkin diagram. And there is a nice combinatorial structure of this Kac-Moody Lie algebra, which is encoded in the root system. So I will recall that. So we have H inside of G is the Cartan subalgebra. And then we have a decomposition of G in terms of the adjoint action of H into weight spaces, root spaces, G alpha. And the root system is in the dual space, maybe a real form of the dual space to this Cartan. And it splits into a real part and imaginary part. OK, that's all we need to know. And how are these differentiated? Well, there are several ways to differentiate it, but one of the main ways to see the difference is that the dimension of G alpha is, well, it's equal to 1 if alpha is real, and most of the time it's bigger, strictly bigger than 1, but in principle it could also be equal to 1 if alpha is imaginary. Okay, so from a Dynkin diagram, one can produce a Lie algebra, and this Lie algebra has a grading, and the weights that arise form a nice combinatorial set. And in addition to this combinatorial set, we also have the multiplicities, okay, the dimension of the corresponding weight space. Okay, and then we also have QG. This is the root lattice. The root lattice.
Could you remind which of these objects are finite or finite dimensional and which are infinite?
So if you start from a simple or semi-simple, a finite type Dynkin diagram, then the Kac-Moody algebra is finite dimensional. Okay, so all the weight spaces are of course finite dimensional. If you start from a generalized Kac-Moody algebra, well, G in general will be infinite dimensional, actually always if it's not a finite type, but each of these weight spaces will be finite dimensional. Okay. Okay, so we have the root lattice, which is the Z span of the roots, and there is a Cartan form on this root lattice. And for any choice of simple roots, pi alpha I, so I would be in the vertex set of this Dynkin diagram. I have a decomposition. I have a positive root system, and then I have a positive subalgebra inside of G. Okay, so for every choice of simple roots, I have a way to say what is half of this algebra. And one can typically consider the enveloping algebra of that positive half. And this is generated by the so-called Chevalier generators, which are EI when I is in I. Okay, and that's all we need to know about the structure of Kac-Moody algebras. Okay. That's a good idea or a bad idea to lift it so high?
No, it's fine.
It's fine? Okay. All right, now let's move on to the quiver side. So we fix K a field. Some people in the room like not to do that and work over rings, but for me, I will just fix a field. And then we can consider the category of representations over the field of the quiver. Okay. And I'm assuming everybody knows that. Am I allowed to do that? What this is? Or should I remind people?
Yes, and when you use the blackboard behind, like the one which is in the bottom now, please write
even bigger, harder. But then how will I erase? Okay. Okay, so let me remind you what this is. So this is objects of this category are pairs Vx when V is an I-graded finite dimensional K vector space, and X is a collection of edges where Xe goes from the starting point of the edge to the ending point of the edge. Okay, so that's the representation of a quiver. If I have something like this, and maybe one loop, and maybe also one arrow like that, it says it's 1, 2, 3, then I will have V is V1 plus V2 plus V3, and then I will have a map like this. This is say A, B, C, D. So A goes from V1 to V2, then B goes from V2 to V3. Then I also have a map going like that. And finally, I also have an arrow like that. Okay, and this forms an abelian category because this is just representation of a certain algebra. Okay, path algebra. All right, so what do we know about this category? So it's not completely obvious, but classical fact. This is of homological dimension. One. Okay, so no x2s. They all vanish. And moreover, if you look at the Grothendieck group of that category, and you equip it with the Euler form, which is dimension of Hom minus dimension of x, which always, as we know, descends to the Grothendieck group, then I can quotient this by the kernel of this form. Okay, this is a so-called numerical Grothendieck group. And this is isomorphic to the, it's generated, freely generated by the class of the simples. So SI is the simple object Vj is delta ijc, if you can see what I mean, and all the maps are 0. This is a simple object. And then these simple objects, they generate this numerical Grothendieck group. And so this is isomorphic to z power I. Okay, and then we have the symmetric Euler form. As I said, which is mn is the dimension of Hom from n to m minus dimension of x to 1 from n to n, plus I just exchanged the roles of m and n. Okay, the symmetrized Euler form. And now we have a symmetric z-valued bilinear form. So we have a lattice. Okay, out of this we get a lattice.
So K0 is before we quote out the kernel of this formula or after?
This is, so K0 is just the usual Grothendieck group, where I just quotient out by the relation coming from short exact sequences. And then when I add the num, I divide out by the kernel of this form. Sorry? Is what? K? Yes, 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 always finite. Yes. All right. So now out of this, I can define a lattice. Okay, I can define, this is just a definition, okay, for the quiver. This is the collection of classes, so it's going to be n, such that there exists an, let's just say absolutely, in case the field is not algebraically closed, indecomposable. Actually, it doesn't change anything. Sorry. There exists an indecomposable K representation of Q of dimension, by which I mean the class in the Grothendieck group, D. Okay, and this is inside n to the I. So I'm looking at all dimension vectors for which there exists an object in this abelian category, which is indecomposable, by which I mean it's not a direct sum of several proper sub-representations. All right, and then this decomposes into what I will call the real part and the imaginary part. And how are these defined? So this is classes of rigid representations. By rigid, I mean x to 1, mm is 0. Okay, representations which you cannot deform. You have to show maybe that, if there's 1 in this corresponding dimension, then all of them are like that. And then there would only be 1. And this would be non-rigid. in decomposables. Okay, so this is purely representation theoretic. I mean, quiver theoretic. Okay. And so let me state this very famous classical theorem, which is due to Gabriel in the 70s and then Victor Katz in the early 80s. Says the following. Well, for every choice of positive roots, there exists an isomorphism of lattices. So not just of Z module, but Z module equipped with a bilinear form from K0 numerical rep KQ to this root lattice, maybe I write G, which sends the class of the simple object to the weight of the generator EI, okay, the simple root. So it means that this is just purely numerical. It's already a strong indication. It means that this Euler form, symmetrized Euler form that I get purely from representation theory of quivers, well, it just matches exactly what we get in representation theory, the lattice of this Kac-Moody algebra. Okay, and both of them, of course, can be very easily computed from the quiver, from the Dynkin diagram. But okay, this is the first indication. Second, more important, so under this isomorphism, what we have is, well, we have delta plus of the quiver is mapped isomorphically, of course, I mean, to delta plus of the Lie algebra. Okay, so, and that's already much less obvious. In decomposables match exactly roots in the Kac-Moody Lie algebra. Okay, this is the Gabriel's theorem in the finite type and then extended by Katz. And what's even better is that this is also true for real and imaginary separately. Okay, so you can also tell if the representation are rigid by looking at whether the corresponding root is real. In particular, you can think has multiplicity 1. And you can see if it is non-rigid, if the corresponding root space has multiplicity more than 1. Okay, or at least is imaginary. So you see that the multiplicity of the corresponding Lie algebra is captured by the complexity of the geometry of the representations of the quiver. Yes?
The labels, should it be on the left side of the board really delta minus re?
Oh, plus, sorry. I'm so used to imaginary. I mixed everything. Yes, thank you.
Sorry, I didn't get it. What is the original connection between the algebra and the quiver? So is the Dynkin diagram interpreted as a quiver?
Yep. If from the quiver you forget all the orientations, then you get a generalized Dynkin diagram. And then out of this, you build a Lie algebra.
Wait a minute. So any non-oriented graph can be interpreted as a Dynkin diagram, not necessarily like
Yes.
the least plus a fine.
No. You have the
like the root added? No.
so there's a notion of generalized Dynkin diagram, and the notion of generalized Dynkin diagram is related to the notion of Kac-Moody algebras. So yes, there is a. Maybe I should have said that. But starting from any graph, even a graph with edge loops, with a loop from going from one vertex to itself, you can associate a generalized Kac-Moody algebra if you want. Okay, and then number 3. So number 3 is even better. Okay, so here we see that, all right, there's this dichotomy between multiplicity 1 and higher multiplicity and real and rigid or actual families of representations. But we can also quantify the families of representations in a nice way, and this is the following theorem. So for any dimension vector, there exists a unique polynomial. So Katz proved that it has integral coefficients, but in fact now it's known as positive integral, and for very good reason. But let me just state the Katz theorem, such that for any finite field, okay, so far K was anything. Now I'm looking at finite fields. The number of absolutely indecomposable FQ representation of Q of dimension D, okay, up to isomorphism, of course. This number is just the evaluation of this polynomial at the size of the finite field. Okay, so it says that the number of indecomposables, I say absolutely indecomposable, those who remain indecomposable when you pass to the algebraic closure, the number of such indecomposables is polynomial in the size of the finite field. Okay, so now we have all the coefficients of these polynomials, right? So that's a interesting invariant. Okay. So what I want to explain now is how we upgrade all of that. Okay, this was known in the early 80s. And then since then, there's been a lot of work in upgrading this. And I think that one could, make the following a very rough picture. This is what I would do if I wanted to get a grant from a big company. Try to, just sell keywords. Okay, so I'm going to claim that what we have seen, at least the very first part of what we have seen, is level 0. Okay, and that's just the numerical Grothendieck group. Rep KQ is isomorphic to this lattice. Okay, and why do I say this is level 0? Because this only concerns the Grothendieck group. So it is some kind, homological dimension is 0 because we kind of semi-simplify. Okay, after semi-simplification, we can say homological dimension is 0. And then we can go to level 1. And here we will have two things that we can do, that I hope to do this morning, is we can do the construction of whole algebras over FQ, or we can do what sometimes people call geometric whole algebra. Let me just say constructible sheaves. So this is over, say, K equals K bar. But let's say FQ bar, although we still have to remember. It's best also to remember the FQ structure, or C. And here we have homological dimension equals 1. And this will produce, the Lie algebra itself. Okay, maybe a quantum version of the Lie algebra. Okay, or the enveloping algebra. So level 0, we just get combinatorics, just the numbers. Then level 1, we consider some things related to homological dimension 1. We will get the quantum group. And then there's level 2, which is where the cohas exist. And this is where we consider cohas. And this is of the cotangent of the category of let me just write this, and maybe I'll explain later. Rep K, yep. Okay, and this will produce a more interesting object than the quantum group. This will be the so-called Yangian. Or we can say it's the loop version of the quantum group. Let's say degenerate version of the loop version of the quantum group. And here we are in homological dimension equals to 2. Okay, and this is where you have the theory of cohas. And then there's a third level that I am personally a bit afraid of, and this is where we really connect to Donaldson-Thomas theory, is we consider the so-called critical coha of, and now I'm going to write something pretty complicated, but I'm not going to. This would just be, to sell the rest by looking very fancy. But I'm not going to say anything about this in this talk, just by lack of time or very little. Is you have to take the shifted cotangent stack to this cotangent stack. Okay, you can also think of it as the cotangent stack of, think of representation of Q as a representation of a certain algebra. Then I'm taking the cotangent stack of that, and I'm taking, in addition, an endomorphism. Okay, I'm taking a direct product with A1 in some sense. And here we are in homological dimension 3. Okay, so the further down we go, the more structure we can get. Okay, and during this course, I think I will more or less stop here, but explain to you maybe at the very end why we do need this. Well, first of all, to prove some statements here, and also to construct some extra structure here that we need. Okay. Any questions so far? Other question? Yes.
Is there some kind of quantum algebra going on in level 3 as well?
So I would say that level 3 allows for many more examples than these. But usually these examples, when you want to compute them explicitly, you kind of have to go down to level 2 again. And then you would get the same. So I would say the examples that are most easily understood at level 3 provide the same algebras at level 2. So it's not so much the algebra, it's just more, you get more structure. But you have, more choices for the algebras, let's say. Okay. All right. So let me go to level 1. All right, so in level 1, let's say first whole algebras over FQ. So we're going to do something a bit more subtle than just looking at the Grothendieck group. We're actually going to look at objects, but it's not going to be very, very geometric because we're going to work over FQ and count points. Okay, we're just going to use that. Okay, so let me, so Q is fixed, right? And let me denote, this is not an innocent notation, but for us it's just one block for the start. This is just a groupoid of representations such that the dimension of M is D. Okay, up to isomorphism. This is a groupoid. Okay, it's best to look at it as a groupoid. And then as a vector space, we're going just to consider the space of functions on that groupoid. Okay, space of functions on isomorphism classes of objects. So sometimes you just write an element, such a function, you just write as a linear combination of characteristic functions. Okay, so there are finitely many objects here because FQ is finite. And so H, let me say Q over FQ is the direct sum, well, maybe for all D of the space of functions on this groupoid. And we can take functions with values in C, it doesn't matter. Okay? All right, and now what we want to do is we want to equip this with an algebra structure. So this is the whole, this is really the heart of all these constructions, is there is, because you are in some nice abelian category, there is a natural construction that you can do. You can look at the set of all, let me write it X. Let me write Q, D1, D2. So let me consider the groupoid of all short exact sequences. Okay, this is all short exact sequences, and I just require that dimension of M is D2, and dimension of R is D1. And of course, the dimension of N is the sum of the two. Okay, so this is also a groupoid. And now what I can do is I can, on the one hand, I can forget about the extension, right, and just remember the sub-object and the quotient. And I get a map Q which lands into MQ D1 cross MQ D2. Or I can forget about the short exact sequence, only remember the middle term. And then I land into MQ D1 plus D2. Let me denote this map by P and the other one by Q. So let's just briefly look at what these maps do. Well, if you start from an object here and an object here, then the fiber is simply the set of all extensions. Okay, so it looks like X1, but you have to be a little bit careful. X1 RM. You have to be a little bit careful because these are groupoids, right? So you have to also take into account the automorphisms. And then it more looks like X1 divided by hom, okay, which makes more, say, homological algebra sense. Okay, that's the map Q. Looks like X1 divided by hom. And then let's look at the fiber of P. Well, suppose I'm given N now, and I want to look at all short exact sequences like this up to isomorphism. You can convince yourself that this amounts precisely to looking at the Grassmannian of sub-representations of a given dimension D2. Okay? So this fiber looks like a Grassmannian, and this fiber looks more linear, like X1 divided by hom. Okay, so later we will upgrade all this picture. I forgot to put the FQ. So there are FQs everywhere. But this picture actually makes sense when you put more geometry. So this. All right. And now, sorry. Wait. Elements of M could have non-invertible. I only keep the invertible morphisms. When I look at the groupoid in this version, I just keep, yeah. So I just want to say that when I consider this map, I should remember that everything has automorphisms. Okay. So now we can define multiplication and co-multiplication. Maybe I move here. So M D1, D2. My notations will simplify over time. Okay. So Q is now disappeared and the FQ as well, and I just remember the dimension vector. Okay, this thing here, maybe I just write like this. HD1 plus D2. And so this is defined like this. To a pair of functions, I associate, okay, there is a certain twist, which is important to have good behavior of the relations and so on. But other than that, it's just push forward, pull back of F tensor G, which means just the following. It means that, F times G of N is, okay, this twist and it's just the sum for all sub-objects of N of F of N divided by M G of M. Okay? So let's just pause for a minute. What did we just do? Well, I take let's just look at what it does for characteristic functions. I take the characteristic function of an object, let's call it R, and an object, let's call it M, and then what I get will be a certain weighted sum of all possible extensions between R and M. Okay? And the weight will be given exactly by counting the number of points of the Grassmannian of subobjects. Okay? So this is a neat way to define, to encode all the extensions between the objects. Okay, that's the whole point of whole algebras, is we use this diagram to create an associative algebra which encodes extensions between objects. Okay.
Sorry, I didn't get it. HD is the space of functions, or is it the representation?
No, HD is the space of functions on MD. Okay. Okay, so here we have a nice associative algebra structure. Now, what's remarkably harder to do in more geometric contexts, especially for Cohas, but very simple to do here, is we can define a co-multiplication by a similar formula. So let me just say that there exists, let me just say because I forgot to write it. I'm sorry, I forgot to write it. So there exists a similar formula for a co-multiplication. But good news is you can get this formula very naturally by what I will now write. Consider the natural pairing on HD. So F, let's say F prime, is going to be, I would write it like this, F prime d mu over MD, but this is a bit provocative. So on an orbifold, you always have a measure, which is just the orbifold measure. You weight by the 1 over the number of automorphisms, but let's say this is just really defined as the sum over all objects of f of m, f prime of m divided by the size of the automorphism of m. Okay, we have finitely many objects, so this is a finite sum, no problem. Okay, and then what can show is that delta, with respect to which delta and m are adjoint. Okay, so if you know a little bit about the junction for these type of morphisms, then from this non-degenerate pairing and the adjunction, you can recover the formula for the co-multiplication. Okay. All right. So this, yes. So this is the two constructions that one can do, and now there's a theorem. So part of the theorem is pretty obvious, and then there's one part which is really non-obvious. Ringel and Green. So let me start with the, let's say, easy part.
We have Q in two different senses.
So there's a small q, which is the size of the finite field, and there's a big Q, which is the quiver. That's the problem.
There is a small Q, which means the morphism.
Yes. Yes. I'm sure you can make the difference, but it's true. It's true. Yes. So here, yeah, it doesn't make sense to take square root of a morphism. So that's my excuse for, yeah. Okay, sorry about that. So HM is an associative algebra. H delta is a co-associative co-algebra. Okay, this was introduced by Ringel, this was introduced by Green. Not so difficult. Once you prove one, you get the other for free because of this adjointness property. And then what's much less obvious, and this was due to Green, H M delta is a, okay, up to some stupid twist, bialgebra, which is much stronger than having just an algebra and a co-algebra. It means that the multiplication is, the co-multiplication is a morphism of algebras.
In this case, do we require the figure is of finite type?
No.
Oh, hereditary, I mean, cyclic.
Ah, I have no relations.
Ah, okay.
I have no relations. And then this is fine. Okay, and because it has a Hopf pairing, I can even say it's a self-dual bialgebra. Okay, so I have an associative algebra which is not commutative because extensions in one direction are not at all the same as extensions in the other. For the same reason, it's not co-commutative. But the beautiful thing is the two glue together into a bialgebra structure which is self-dual. Okay, so these kind of things we tend to call quantum groups. It's pretty general, but vague, but that's what we call quantum groups. Okay, and now let me, so what we want to do, we want to understand the structure of this algebra. Want to understand what is the structure. So maybe before that, I just want to note, by construction, what is the dimension of this algebra? So graded dimension, by which I mean the sum over all d of the dimension of hd z to the d. Well, what is this? This is the sum for all d of the cardinality of the set of objects. Okay. Up to isomorphism, z to the d, obviously. And, well, I put it all in a generating series because now I can express this in terms of generating series of indecomposables, because every object is a direct sum of indecomposables in some unique way of, not canonical, but the terms, the factors, and their multiplicities are unique. So that would be for every indecomposable. So I can just put them together according to the dimension. And I get the number of indecomposables of dimension d. And here I just do some kind of magic that I have a feeling will not go well in. I'm going to have to explain some stuff, I'm afraid. So it is some platistic exponential over all d of this number of absolutely indecomposables. Okay, so here we have the Katz polynomial counting absolutely indecomposables. And this is the so-called platistic exponential. And, well, it plays a role, but it so let me try to see if anybody stops me. If I don't put the q here, it means you can take it as a definition. It's a product over all d of 1 over 1 minus zd to the power aqd of q, okay, which is a number. Okay. And yeah, no, I should be, yeah, that doesn't make really sense. Oops. And then I put t equals q. But now there's a small game you have to play between counting indecomposables and absolutely indecomposables. Okay, you may have an indecomposable FQ representation which splits over FQ bar into a sum of indecomposables that would be Galois conjugate. So when you pass from this expression to an expression which involves absolutely indecomposable, you have to take into account all of these ways of splitting an indecomposable. And let me just say that this is taken care of by this beautiful platistic exponential. Let me move on to the next topic very quickly. But so maybe I just give an example, a serious example of what this platistic exponential does. Let V be a n L graded vector space. Okay? Then let us look at the sum for all n greater or equal to 0 of the graded dimension, and let's say, yes, and the sum for all, no, let me not write that. The sum for all tuples n of the graded dimension n of V, no, sorry, yes, yeah, of the symmetric algebra of V, and then let me put Z to the n. Okay, so I have a bunch of variables taking into account the graded dimension of all these, of this vector space. Okay, and I form a generating series where I look at the graded dimension of the symmetric algebra. Okay. Then this is given by the platistic exponential in the variable z of the graded dimension of the graded dimension, well, let's see, sum over n, graded dimension of V, z to the n. Okay, so platistic exponential is exactly the combinatorial machine that takes the graded dimension of a graded vector space and spits out the graded dimension of the symmetric algebra of that vector space. Okay. So in some sense, if I have a Lie algebra here, G, then here I would have the enveloping algebra of the Lie algebra, which by the PBW theorem we know as a vector space is isomorphic to the symmetric algebra. Okay, so that's the intuition. Okay, so 10 more minutes. So let me just briefly say, this is, this has nothing to do with quivers really. It's just some combinatorics of field extensions. So we have an algebra, a bialgebra, self-dual, looks like a quantum group. And we know that the graded dimension is encoded by the Katz polynomial. And moreover, we know that it looks like the graded dimension of the symmetric algebra of a certain algebra, at least vector space. So now we want to understand what this could be. Okay. So let me state some theorems. Maybe one more remark. When you look at this, you may get a little bit scared because, okay, we have a nice algebra. It depends on Q. So if you're used to quantum groups, you say, okay, maybe it's just going to be the quantum group and Q is the quantum parameter. But there's one point that you have to remember is that this is the size of the algebra. The size of the algebra depends on Q. Okay? So yeah, it's not just going to be a quantum deformation of one algebra because the size actually does depend on Q. So, easier problem. So the structure of HQ over FQ. Okay, that's a natural question. And we first look at a simpler, or let's say more canonical, maybe a subalgebra, a certain subalgebra, which I call the spherical Hall algebra. And it's the subalgebra generated by the easiest functions. in this algebra, which are just a characteristic function of the simple objects. Okay, so I look just at dimension 1, at one point of the vertex, 0 everywhere else, and I get some natural functions. I have no choice, essentially no choice. And so here's the theorem by Ringel, again in finite type and green. In general, it says that this algebra now, well, first of all, the size of that one does not depend on Q. That's already non-trivial. But this is isomorphic to the positive half of the quantum group, okay, corresponding to the Lie algebra, G associated to my quiver.
You need to take some square root.
I mean, I didn't say what UQ was. But OK, to please you, let me put a square root. And this just sends the generator EI to up to some normalization, 1 SI. Okay? So at least there is a small thing inside which is independent of Q and which recovers the quantum group. So we're very happy because we got out of the quiver more than just the Cartan matrix. We actually got the quantum group itself. And so that's very good. Maybe let me just say, OK, I have 8 minutes. I have 8 minutes. 8 minutes. OK, I can do it. So let me give a quick idea of the proof. First of all, there exists, oh wait, this is a bi-algebra, right? Bi-algebra. Isomorphism. Okay, so there exists a bi-algebra isomorphism. There exists a bi-algebra morphism. This is easy, and the morphism goes like that. Okay, so this is easy because this is very simple computations. I just have this is generated by these EIs, so I just have to perform extensions of simple objects and see how they extend. Okay, so you cannot understand the theory of whole algebras if you don't do this by yourself, but it's beautiful that you recover the same relations as in the quantum Serre relations. Okay, so there exists a bi-algebra morphism, and you just look at what it does on the coproduct. And therefore, so you need to know one thing, is that there exists a non-degenerate Hopf pairing on UQ plus N. You can present it like that, which is called the Drinfeld pairing. Okay. And therefore, the kernel of psi, let's call this. Kernel of psi is an ideal and co-ideal of UQ plus of N, and which does not intersect of course, the piece in degree 1 in dimension 1. Okay, and then from quantum group theory, it's not so hard to see that this is not possible. Okay, this is not possible. UQ of N does not possess many ideal and co-ideals. Okay, take an ideal, take the smallest degree possible. If it's not of dimension 1 of these, you can break it up into further smaller piece. Okay, and so so when you have all this structure and the pairings are compatible, maybe there exists a compatible. Okay, alternatively, another way of saying it, which which, yes, another way of saying it is that using duality between multiplication and co-multiplication, you can say that when I look at the spherical whole algebra and I look at what I call delta max, which means I have a dimension vector d here. I look at all possible graded components of iterated of the coproduct, which land into a tensor product of dimension 1 parts. Okay? So I just write like this. The tensor algebra of the direct sum over I of, let's say, H alpha I. Okay? So this is an embedding. You can also phrase the existence of the non-degenerate Hopf pairing on this spherical whole algebra by saying that this is an embedding. And in fact, this, we can equip it with an algebra product, which is a shuffle algebra product, which was introduced by Marc Rousseau a long time ago, which makes sense in any braided tensor category. And so you can realize, thanks to all these structure, you can realize the spherical whole algebra as a certain very specific subalgebra of a shuffle algebra, purely combinatorial thing. Then you can do computations there. And we will see that this is something that survives in the Coha world, in some sense, and which turns out to be actually very useful. But here, it's not so apparent, but it really is it's just the same. And let me, I have some time. So let me state one other theorem, which, which is, let's say, the person who put the last piece in the proof of this theorem is Tamas Hausel. And this is kind of equivalent to the so-called Katz conjecture. The first conjecture, 1, is the following. It says that, well, now let's look at the graded dimension of this spherical whole algebra. So we know that when I look at the entire whole algebra, right, and look at the graded dimension, I get this thing, which corresponds to the Katz polynomial. And that's pretty easy to show. Okay, I more or less explained the proof, except for the very last step. So now we could say, well, what is the graded dimension of this subalgebra? We define some natural subalgebra. We see that that subalgebra does not depend on Q. Good. And also it's pretty natural. It's a quantum group. It's generated by some very simple objects. And so the theorem says that, well, this is the platistic exponential of AQD of 0, just the constant term. Okay, only constant term. So somehow this spherical whole algebra, it amounts to just, in this big algebra, just picking out the piece corresponding to the constant term of this Katz polynomial. And what does it, what does it say? And this was the statement of Katz conjecture. It says that when I look at the constant term of this Katz polynomial, well, this is precisely the multiplicity of the corresponding Lie algebra. Okay, the dimension, this is defined. Oops. On this side, this is defined as the dimension of G T. Okay, so this is really amazing conjecture, I think. It tells you that counting over finite field absolutely indecomposable representations of the quiver, which is like a purely geometric problem, then taking the constant term, which seems like it doesn't make any sense because maybe the leading term makes sense, but that we don't know how to compute it. But taking the constant term seems like it's a pretty strange thing to do. Well, that recipe gives you some number which is hard to compute, which is this multiplicity in the Kac-Moody algebra. And this works for any Kac-Moody Lie algebra. So that's really nice. And so let me just finish by asking a question that I will answer in the other parts of the lecture. So a natural question. Well, does there exist a, let's say, graded version, maybe, let's say, h tilde q over fq, such that, so by graded I mean not just that the dimension depends on q as a polynomial, but actually a graded vector space, n-graded vector space, such that when I look at this graded dimension of h tilde q over fq, I really get the entire Katz polynomial of t now, z to the d. Okay, and so here the grading encodes both the grading, the extra grading, and of course the grading by the Grothendieck group. Okay, that's the first question, and then the second question is AQD of t equal to the multiplicity of some other algebra, okay, of D for some Lie algebra, some graded Lie algebra, J tilde, of course, such that J tilde in degree 0, let me say, this would be the extra grading, would just be our Lie algebra G. Okay, so can we construct a graded version? Can we actually have this? And yes, so the answer will be that this looks like a natural question, and there is an answer to that. But it's actually even better to go one level up, pass from homological dimension 1 to 2, and we will get something slightly bigger than that, which will also be very interesting. Okay, but we will be able to extract the answer to this question from something that will yield an algebra, even a bigger algebra. And let me stop here.